Hello there. Let's take a look at section 5.7 today, where we're using the second derivative test to determine relative local mins and local maxes. So this is another way that we can find mins and maxes if we have the second derivative. Sometimes you have information about the first derivative, but not enough that we can create a sign chart. And so here's where we'll come in with another alternative method. So the first derivative test of relative extrema, we remember that we would find the critical values, find where f prime was equal to 0 or where it did not exist, and then take it into a sign chart. And then we look at the critical values. Local min, of course, occurred where our sign chart changed from negative to positive, and local max from positive to negative. So that's just a quick review of these in the first derivative test. The first derivative test was really very straightforward, generally quick and easy to use. However, it doesn't always work. So in order to use the first derivative test, two things had to be true. We had to be able to find the critical values of f of x, and we also had to be able to determine if a sign changed of f prime, and then what that direction of change was, negative to positive, positive to negative. So what do we do if we can't use a first derivative test? Well, if we can't use the first derivative test, there may be another way to find that extrema. So let's just consider this. Consider an f of x where we're not given the equation for f of x. However, we do know that f prime of 2 was equal to 0. What does this tell us about f of x? What does this not tell us about f of x? So if we knew that f of x, or f prime of 2 equaled 0, that means it is a critical point, right? And that there is a potential place for a relative min or a max. Now, I don't know exactly what's going on with f of x here, but I know either I'm entering into f prime of 2 where it's equal to 0 with a concave up style, and in that case we can see that this location would be a relative min. If I entered into this location with a concave down, then I'd have a relative max at that. And the third possibility is perhaps I enter this with a changeover with f double prime also equaling 0, where I'm changing from concave down into concave up or vice versa. If this is the case, then neither is happening. I have neither a min nor a max. So in the above example, what if we also knew that f double prime of 2 was equal to negative 5? What would that tell us? Well, if f double prime of 2 equals negative 5, that tells me f double prime is negative and therefore concave down. So I would have two pieces of information. I would know that f has a horizontal tangent line because I was given the fact that it was equal to 0, the first derivative. And if I was given information, or I could discern information about the second derivative, I'd be able to know its concavity. And in this case, I would know, I would have case number 2. And I'd have a relative max then at x equals 2. This is the idea behind the second derivative test. So here is kind of formally the second derivative test of relative extrema. Consider a function f of x with f prime of c equal to 0. So we know our first derivative is 0, which tells us we have a critical point, right? You might even want to just make a note. Therefore, c is a critical point. And if I know that f double prime of c is greater than 0, then I know that f of x has a local minimum at x equals c by the second derivative test. And if f double prime is less than c, then I have a relative maximum at c. So maybe even I think it might be helpful if the second derivative is greater than 0, I have concave up. If it's less than 0, I have concave down. And then that should allow you to see that, Concave up means minimum, concave down second derivative means maximum. If it happens that f double prime equals 0 or f double prime is undefined, then the second derivative test is inconclusive and we cannot apply it. F of x may have a local min, local max, or neither at x equals c. The first derivative test should be applied if possible. Otherwise, I just will not be able to determine max and mins. Another important note, the second derivative test is a test for relative extrema, not for points of inflection. The first derivative test and the second derivative test are both relative extrema, and that really has more with naming conventions. If I refer to the second derivative test, I don't want you to think that's going to be talking about points of inflection or concavity. Below side-by-side comparison, you can read through that. And when should we use the second derivative case? In most cases, use and apply the first derivative test to find values of x where f of x has local extrema. However, there are two cases that appear on the AP exam that will require you to use the second derivative test. That's like when you're working with the table of values, also when working with an implicit curve. Okay, so that's going to be like the dy, dx stuff. Also, I can think of another time is when they don't provide you with the function, so you can't take a first derivative and make a sign chart. All right, so let's go into using a chart, because we said that's one of the ways that the AP exam will force you into the second derivative test for relative min and max. So example A, identify all x values where f has a relative min. Justify using the second derivative. So when I'm looking for x values where f has a relative min, the first thing I want to look at is f prime equal to 0 anywhere? And I'm getting two spots where x is 2 and where x is 7. Now, what I also need to have is that for a relative min, draw the picture. What do I need about the second derivative? For relative min, I need concave up. So which leads us to that? When x is 7 or when x is 2? Where would I have concave up? Well, I'm going to look at the second derivative, right? And the second derivative, either I'm looking at 4 or I'm looking at a -3. Well, this is the one that's going to be concave up. So a relative min of 7 occurs, I was thinking of saying 7, so it took me a moment, sorry guys. A relative min of 7 occurs at x equals 2 because we know the first derivative evaluated at 2 equals 0 and the second derivative evaluated at 2 equals 4. So f of x is concave up. And that would be our justification. Notice that we had to talk about the first derivative as well as the second derivative, and I'd also mention the fact that it's concave up. Part B, identify where we have a relative max. Well, that is probably going to be here when x is 7, right? And we come out with a -2. We knew that we had a critical point, and we knew in this region we're concave down, so that should confirm a relative max of -2. The y value occurs at x equals 7 because f prime of 7 equals 0 and f double prime of 7 equals 4. So f of x is concave down. Identify all the x values where f has a point of inflection. Can I get that off the chart? Yep, I should be able to get that off the chart. I'm going to clear my ink, and now what I'm going to focus on, if I'm working on points of inflection, that comes from a second derivative. And I have to have sign changes for second derivatives in order to get a point of inflection. We need to change from concave up to concave down, or vice versa. A point of inflection occurs at x equals 5 because f double prime changes sign at x equals 5. So we needed to have, I think I forgot to mention, the fact that f double prime had to equal 0. And then I had changing from positive to negative on each side of 0. This particular 0, I don't have enough information to know if we're changing sign, to know if I'm going to switch concavity. Okay. So this is really just an additional question, doesn't really pertain to this particular section, just previous information or previous stuff we've covered. Part D, also previous coverage. What is the equation of the tangent line? Equation of the tangent line to the curve of y equals f of x at x equals 5. Okay, so at x equals 5, I'm going to be focused in on that column. I'm going to need to reference probably f of x and f prime. Why don't you hit pause, see if you can write this out. I know that f of 5 was equal to 3. I know that f prime of 5 was equal to -1. This gives me a point, doesn't it? I have the point 5 comma 3, and this was giving me the slope of my equation. Super easy. We can do this in our sleep by now, and we get -1 x minus 5. And that should be the equation of our tangent line.